morning, ladies and gentlemen. We are from Nanyang Technological University, Singapore. My name is Ren Ye. This is my teammate Kuo Hong and Jian Hao. We are going to present to you a distributed vehicle-to-vehicle charging system. This is the outline. We would first like to introduce to you the concept, and followed by our proposed system, and then the simulation of the system, and finally is a summary and the future work. So why do we need electric vehicle? Because as we see from the curve, we can see that the oil price is going to be rising in the next decades, and in the meantime, the carbon dioxide concentration is also rising. It is partly due to the conventional combustion engine powered vehicle. And on the other hand, there is a forecast on the on the future of the electric vehicle. We can see that in the next decades, there will be a large boom of production of electric vehicles, especially in Asia Pacific, Europe, and North America. This slide shows the existing charging schemes for electric vehicle. Basically, there are two types. One is grid-to-vehicle, and the other is vehicle-to-grid. For grid-to-vehicle, the concept is quite simple. When we plug in an electric vehicle, it will draw power from the grid. Now, there's an improved version with smart charging. There will be a smart controller to avoid the charging during the peak hour to minimize the impact on the power grid. The vehicle-to-grid is the other way around. That is, the electric vehicles will send power back to the grid. Either it can be you treat all the electric vehicles as remote batteries for power balancing, or some hybrid vehicles such as solar cars or hybrid or fuel cell vehicles. They can be used as a distributed generation. So why do we need to propose vehicle-to-vehicle charging? Because it can avoid the construction of the charging stations, and it is easy and flexible to be set up in our home grid. It is also convenient for the electric vehicles owners to charge and manage their car charging, and it will also minimize the negative impact to the power grid. Our proposed system has two parts. One is the distributed computing, and the other is the optimal scheduling. For distributed computing, there are two kind of modes. One is a cluster-based master-slave mode, and the other is a parallel computing mode. And for the optimal scheduling, it is a nonlinear constraint and nonlinear objective function optimization problem, and I will introduce to you in the next few slides. Let's view some. This slide shows the illustration of distributed computing with cluster-based master-slave mode. Inside this car park, there is a master car that will calculate the optimal schedule and send the optimal solution to the rest cars as a slave. And they will follow the optimal schedule for charging and discharging. If there are more than one clusters, there will be one master for each cluster. Another setup is called parallel computing. The optimizing job, the optimal scheduling job is distributed evenly to all the cars, and every car can calculate the optimization solutions by their own, and the final solution will be combined together to find the global minimum. So what is optimization? In a simple point of view, it's just to find the minimum value of a function subject to some linear or nonlinear constraints. The conventional optimization for constrained nonlinear optimization has interior point, sequential quadratic programming, active sets, and trust region reflective setup. But their limitation are on the objective functions and constraints, especially for non-differentiable, highly nonlinear, stochastic objective functions. Therefore, we would like to use a genetic algorithm to overcome those problems here. So what is a genetic algorithm? It is an algorithm that is developed from natural selection. First, we have a set of population of solutions, and these solutions will repeatedly modify and produce itself towards the optimal solution by crossover and mutation. However, this genetic algorithm cannot guarantee a unique minimal solution. But the advantage is that it is very simple and it can be parallelized if we have multiple processors. So back to our project. This is our optimal scheduling problem. We would like to maximize the electrical vehicle charging towards their rated capacity for each. And in the meantime, we also like to avoid overcharging and also avoid the overconsumption from the grid. So the final optimal schedule is this delta K and N. Here shows a simulation setup. We randomly draw samples from 6 available electric vehicle models, and we set up input set with, let's say, 10 electric vehicles with inertial and rated capacity, and their plug-in and plug-out time from the grid, and also the available grid power. And this one shows the MATLAB GA toolbox output. If we rearrange the solution, it shows the charging and discharging profile, where the blue one is charging and the red one is discharging. So in summary, our proposed vehicle-to-vehicle charging system with GA optimization is able to show a feasible implementation of the system, and it can avoid the station controller. The future work will be, we would like to consider more on this variable power charging. That means non-consistent charging voltage and current. They will be variable, they will be dependent on the state of charge. And we would also like to consider temperature facts and transmission efficiency and battery lifespan, and even economy issues. Maybe for different cars, you have different priority, but they need to be put on more penalty. And that's the end of our presentation. Thank you. Do you have any questions?
In your optimization scheme,
yes.
Did you take into consideration the behavior of the users?
Yes. Yes, the users, they can set up, they can manually interrupt on this plug-in and plug-out time. And also they can interrupt on their charging and discharging power. It can be set up by the user, otherwise it will be a default value.
Yeah, I'm curious about your methodology. I
Yes.
believe the first of all, you have to identify what would be the major factors affecting your capacity, okay? And secondly, I believe in the earlier your presentation, you mentioned about the methodology, you mentioned about the minimize something.
Yes.
And this one, you to maximize something. So I think you have to use dual objective. Okay, maximize the benefits and minimize the risk or the environmental concern.
Okay, for optimization, here is just an illustration of minimize. And if we want to convert maximize to minimize, we just add a minus sign here. This is a kind of single objective minimization. And if we want to put penalty on different vehicles, we have here the penalty factor for each vehicle. So if they want to optimize more on specific vehicle, we will put more on their penalties.
Yeah, I think for this kind of the research work,
Yes.
from the environmental, the life cycle assessment, we have to minimize economic benefit.
Okay, yeah, I see. Yeah, thank you for your suggestion.
Yeah, I'd like to confirm that how much physical experiment you have actually done. Now, this it seems that you have developed the software.
Yes.
Have you tested it on real cars or real systems?
So far, we only on the simulation stage.
So it's all computer simulation.
Yes.
Never physical experiments.
So far, we don't have. We haven't go into this step.
Thank you.
Yeah. So the demonstration is on software simulation, and we are running with MATLAB and GA toolbox. So our concept is to use GA to optimize the objective function subject to nonlinear constraint. And here is the setup, and we random draw samples from 6 available commercial electric vehicle models, and we have 10 vehicles set up with 6-hour time span, and 5 vehicles set up with 12-hour span with different grid power supply and also different parameters. Here I will just click on the run, and the MATLAB toolbox will automatically do some G algorithm to do the optimization. So since this is a MATLAB code and the GA, and also the GA algorithm is well developed, it can be recoded into C++ or other coding, and it can be integrated to vehicle's microprocessor. Maybe the vehicle is running on ARM, and it can be used C++ to do the software upgrading. And the advantage is we can only do software upgrading to make our system work with the existing electric vehicle. And I will show you this. This is a 5 EV setup. This is a variable grid power. I will add a random noise to the grid. It has a rising trend. This is a random sample with a normal distribution, the plug-in and the plug-out time of the vehicle. This is a uniformly distributed, uniformly random sampled vehicle initial capacity and rated capacity. After GA, it gives the optimal charging scheme. The blue bar is charging and the red bar is discharging.
When you say optimal, and you also say that you don't get power from the grid, right? So you are sharing the power among all these vehicles?
The objective is to do not avoid over-consumption from the power grid. So here we have some available power as shown in this figure. So the total power draw from grid will not exceed available power.
So the power still comes from the grid.
Yes, we can
You're
also
just trying
modify.
to find the best way to draw power.
Yes,
from the
without much power loss or voltage deviation. And this configuration can also avoid the power grid of, let's say let's say if in a car park without power grid.
My question is, if you're still taking power from the grid,
Yes.
why do you call it V2V?
This setup, the grid is optional. If we don't have the grid, we can also optimize based on the user's preference.
Because if it's V2V, that involves taking one energy from one car to another. So there will be monetary.
Yes, yeah, we can sell power to